In this video, we're going to look at Boltzmann distribution curves. These are basically graphs of a mathematical function that describes the distribution of speeds or kinetic energy of the particles in a gas. You must be able to sketch and label these curves and understand what these graphs represent. You will need to explain the effect of a catalyst on the rate of reaction using one of these curves, and also explain how the temperature affects the shape of these curves and therefore affect the rate of reaction. You must also be able to explain these effects using the correct keywords and phrases. Boltzmann distribution curves, often called Maxwell-Boltzmann distribution curves, are worked out from a mathematical function that we don't need to calculate for A-level chemistry, but the curves basically serve as a model to explain the effects of temperature or catalysts on the rate of reaction. In a gas or liquid or solution, the particles within it don't move at the same speed, and therefore don't have the same kinetic energy. Some particles will have more energy than others, but most of the particles will move at a speed close to the average speed. If you know anything about maths or probability, this is a continuous probability distribution. If you don't do A-level maths, don't worry. All you need to do for A-level chemistry is sketch these curves, label them correctly, and try to understand what the parts of the curves represent, and then use them to explain the effects of catalysts and temperature on the rate of reaction. So let's look at one of these curves. On a Boltzmann distribution curve, the x-axis is labelled kinetic energy or energy, and the y-axis is normally labelled number of particles, or even better, number of particles with a given energy. Now there's three things that you must remember when you draw these curves or sketch these curves. That first of all, there's no particles with zero energy, so this curve must always touch the origin, and you always label this zero. Secondly, there's no maximum energy for a given particle, so this curve never touches the x-axis, except at the origin. Finally, the total area under the curve, it's under this curve here, or this area, represents the total number of particles in the system. If I use an analogy that you may have done at primary school or secondary school, it's easy to understand why the area under the curve represents the total number of particles. So you may have done at school in biology, measuring the heights of different people in the class, and drew one of these sorts of charts to show the distribution of heights of the people in the class. And I'll probably be down here. So you only have one person here with this height range, and two people here with this height range, and five with this height range, and so on. So you can see on this graph that the area here represents the total number of people. So, 1 plus 2 plus 5 and so on will give you the total number of people. So back to our Boltzmann distribution curve. As we said, the area under the curve, or the total area under the curve, represents the total number of particles in that substance, which is usually a gas, in the case of Boltzmann distribution curves. So what I've done here is, on the energy scale axis here, I've put in a line to show the activation energy for a reaction involving these particles. So therefore the area under the curve beyond this activation energy line will represent the total number of particles that have sufficient energy to react. So the area under the curve and above the activation energy, area under the curve above the activation energy, represents the total number of particles that exceed the activation energy and so can react. So that's the sort of wording you would use to explain this area here. So let's look at some of these labels I've put on to remind ourselves what the Boltzmann distribution curve shows. So first of all, we must remember that the line always touches the origin. And what does that represent? Well, it represents that there are no particles with zero energy. Secondly, here, I've shown that this line never touches the x-axis again as it carries on into infinity. And the reason for that is there are always some particles with very high energy. There's no maximum energy limit for those particles. And the area under the curve, as we said, represents the total number of particles of a fixed mass of gas. Before we move on to look at how we can use Boltzmann distribution curves to explain how a catalyst will affect the rate of reaction, I thought we'd look at some of the other features of the Boltzmann distribution curve using an analogy of the heights of people of the class again. So we can see here the most likely range of height is this one here, and there are very few people with this height range, and there are very few people with this height range. So if we compare this with our Boltzmann distribution curve, hopefully we can understand this curve a bit better now. So the most likely energy for a particle in this system would be here, because most of the particles, there's the number, have this energy, and there are very few particles with low energy, and again very few particles here with very high energy. So hopefully you can understand what this graph really represents from looking at the analogy with heights of people in the class graph. So now we understand the Boltzmann distribution curve a bit better. Let's look at how we can use this curve to explain the effect of a catalyst on the rate of reaction. So here I've sketched a Boltzmann distribution curve with the correct labels and with the correct features. I've also labelled the activation energy for an uncatalyzed reaction, so there's no catalyst in this reaction. And the blue shaded area here, crosshatch here, will represent the total number of particles that exceed the activation energy. So therefore, this is the total number of particles that could react. Now, what does a catalyst do? Well, a catalyst, as we know, lowers the activation energy. So this line here, which is lower in the energy scale, on the kinetic energy scale, will represent the activation energy for the catalyzed reaction when we add a catalyst. So the shaded area here, or the crosshatch area here, which goes all the way through here, by the way, so it's not just this area, which some people do in the exam by mistake. You must draw the cross-hatching across the whole of that area. That area here represents the total number of particles that exceed the activation energy and therefore can react when you add the catalyst. And you can see from the graph the area under the curve above the activation energy or beyond the activation energy is higher, is greater for the catalyzed reaction compared to the uncatalyzed reaction, which has a smaller area under the curve above the activation energy. So that represents a smaller number of particles that can exceed the activation energy and react. So in any given time, there's only a smaller batch of particles with enough energy to react. So every second there'll be a smaller batch of particles that can react. If I have a catalyzed reaction, every second there'll be a greater proportion of particles that can exceed the activation energy and react. So those particles will convert at a much faster rate into the products. Hopefully remember that the energy of the particles is not fixed. So I've said this on a previous video with the animation of the cars. So a particle can collide initially with another particle, but not with enough energy to react, and they bounce away from each other. But in subsequent collisions, energy is passed on between particles. So that particular particle, which could not react earlier, could have gained more energy in subsequent collisions in order to exceed the activation energy and react. So eventually all the reactants could react. If you give it long enough time, they could all react. So here I've given you the sort of wording you would use to explain why adding a catalyst will speed up a reaction. So adding a catalyst lowers the activation energy by providing an alternative reaction pathway. So we must say that phrase. So we must say what a catalyst does and how it does it. Then we need to say this increases the area under the curve and above the activation energy. So we must refer to the Boltzmann distribution curve. We can't just ignore that, otherwise you've not really answered the question. So this increases the area under the curve and above the activation energy. So area under the curve above the activation energy. So next thing is this keyword proportion or greater proportion, the key phrase here. A lot of people miss that out and lose that mark. You must say a greater proportion of particles will exceed the activation energy in a given time. So a greater proportion of particles exceed the activation energy in a given time or per unit time. What I mean by that is, per second or per minute, whatever. So increasing the frequency of successful collisions, because as we said in the previous video, a successful collision is one that exceeds the activation energy and leads to a reaction. So this is the sort of wording you should use in your explanation. The most common mistake people make when using the Boltzmann distribution curve to explain how catalyst works is that they say, instead of greater proportion of particles, they say more particles exceed the activation energy in a given time. And that will be marked wrong. You won't get a mark for that. So you must say greater proportion of particles rather than more particles. Okay, let's look at what happens when we change the temperature to the Boltzmann distribution curve and how we can use that to explain why the temperature affects the rate of reaction. So here I've drawn a Boltzmann distribution curve with the correct features, with the line meeting at the origin and nowhere else would it cross the x-axis here. And we got this peak. This is the modal kinetic energy the particles will have, and we got here marked on the graph already the exponential energy for the reaction. Now there's no catalyst in this case. We're just looking at what happens when we change the temperature to this curve. Now the shape of the curve would change when you change the temperature, and that makes sense because if you raise the temperature, for example, more of the particles will have a higher energy. So this peak here would be, well, would it be here or would it be here? Well, high energy, it's on this side. So this peak of the curve will shift towards the right hand side, towards high energy with an increase in temperature. Now, the next thing I always think about, if the peak moves across there, this peak will not be at the same height, and the reason is we must have some particles at zero energy. So this line basically must be fixed, must be connected to this point here. I'll show you a way to understand that. Before we do that, what I mean when we increase temperature and the peak shifts across is something like this. Now, this won't be the correct way to sketch the Boltzmann distribution curve at high temperature, and the reason is this height cannot be the same as this height, and I'm going to explain that next. So one way to explain this is imagine you draw your Boltzmann distribution curve on a piece of elastic and you can stretch it. So you can see I'm stretching this curve towards the right hand side. You can see the peak going towards the right against the blue markers I've drawn at the top there. Now in this case the height hasn't changed. If I go back and stretch it again, the height hasn't changed for that peak. And you notice the area, the white area, is actually increased. And we can't have that in the Boltzmann distribution curve because the total area under the curve represents the total number of particles in the system. And you can't increase the number of particles in the system, it's fixed. So that area must stay fixed as that peak moves towards the right. And the only way to do that is for the height to come down to keep the area the same as that peak moves to the right hand side. So you can imagine if you were to draw this peak on a piece of elastic band and then stretch it, you can imagine that as you stretch that elastic band and stretch the peak towards the right hand side, the stretching would cause that elastic band to flatten as well to maintain the same area because you still got the same number of particles in that material. So at high temperature, which I've labelled as T2, the Boltzmann distribution curve should have its peak at a higher energy on the energy scale or kinetic energy scale. But the height of the peak must be lower than that of the lower temperature. It seems a bit strange because at higher temperature you might think this is higher, but it's not. It's actually lower. At the lower temperature T1 here, the peak is taller, but the peak is at lower energy on the scale for energy. So how can I explain using the Boltzmann distribution curve that increase in temperature will increase the rate of reaction? Well, you can see it for the curve at high temperature, the area under the curve above the exponential energy is actually greater or larger than the area under the curve above the exponential energy for the lower temperature one. So this means there's a greater proportion of particles that exceed the exponential energy in a given time that will react. So there's a bigger batch of particles every second of the reaction that will exceed the exponential energy and convert to the products. So I've written here, increasing the temperature increases the area under the curve and above the exponential energy. So I've referred to the Boltzmann distribution curve, otherwise I'm not really answering the question if I'm asked to explain how the temperature affects the rate using a Boltzmann distribution curve. I must refer to the curve. So here's the key phrase again. So a greater proportion of particles exceed the exponential energy per unit time or in a given time. So if you say more particles exceed the exponential energy, you won't get the marks. You must say greater proportion of particles exceed the exponential energy. So what happens with greater proportion of particles exceeding the exponential energy in a given time? well, we get an increase in the frequency of successful collisions, those collisions that lead to a reaction. So what will happen if I lower the temperature compared to that of T1? Well, hopefully you would know that the peak of the curve would be towards lower energy on the scale of energy. And in order to keep the total area the same as before, because the total area is the total number of particles of the gas or of the substance, and that can't be changed by changing the temperature, the peak would be taller. So what you see then is this, and you can see that the area under the curve above the activation energy for the lower temperature, which is T3 here, is smaller than that of the initial temperature T1. So decreasing the temperature decreases the area under the curve and above the activation energy, so a smaller proportion of particles exceed the activation energy per unit time or in a given time. So decreasing the frequency of successful collisions leading to a slower reaction. So again, it looks a bit strange that at lower temperature this peak is taller, but remember this peak is at a lower energy, and in order to keep the total area the same, which is the total number of particles in the system, I must have the peak being taller because it's narrower. Just a short note, throughout all my explanations I've used EA as an abbreviation for activation energy. In the exam you should really write it out once in full before you abbreviate it, so I got away with this by putting it on a key at the start of the explanation when I first used it. So we looked at how to draw and label Boltzmann distribution curves and hopefully understand what the parts of the curves mean. And then we use these curves to explain the effect of a acid on the rate of reaction by focusing on the proportion of particles that exceed the activation energy in any given time and how that increases with lowering the activation energy. And then we looked at how the shape of the Boltzmann distribution curves change with temperature and therefore affect the proportion of particles that exceed the activation energy at any given time and therefore affect the rate of reaction. And finally, we looked at some of the key phrases and words we must include in order to meet the marking criteria in the exam.